So today I will talk about how to accelerate cloud training with Elastic. Basically, how could we make our GPUs busy? And already introduced me, so I will skip these slides. So for today's agenda, I will talk about what is Elastic and its POSIX API. Basically, how can we, without modifying our training script, can access data in our cloud storage? And then I will talk about the 3 levels of how to accelerate cloud training with Elastic, how to accelerate our cloud storage rate, and how to combine the data preprocessing and training together, and then how to make all the computes and cloud storage connect together to become a data orchestration layer for our whole training process. So first about the Elastic and its POSIX API. For some of you guys that may not familiar with Elastic, Elastic is a data orchestration layer for analytics and AI in the cloud. Basically, on the top of Elastic, you can run different compute, ETL, and training frameworks, especially like TensorFlow and PyTorch. And underlying, Elastic connects to all the different kind of storage system, including the popular like S3, Azure, and other HDFS clusters. And Elastic basically creating a unified namespace for all the compute and training frameworks to access different cloud storage and providing caching abilities. So that's because we provide different interfaces for connecting to different compute frameworks. For example, we provide the POSIX interface for our cloud training, especially TensorFlow and PyTorch. And Elastic provides data caching capability. So for example, our training and our compute may be on the cloud, and our data storage may be remote, or maybe in a remote like HDFS cluster, or maybe the remote cloud storage. So by using Elastic, we can basically like get the data from our remote object storage and cache the data locally to provide local performance for repeated data access. And similar for metadata, we can also catch in the metadata locally. And for Elastic POSIX API, basically Elastic create a unified namespace for different storage system. And Elastic POSIX API made one step further. We can access different cloud storage, not using Elastic's APIs, but using our standard POSIX API, like the make directory, nkdir command, ls command, and all the Linux command that you guys are familiar with. And all the training frameworks like PyTorch, TensorFlow can directly access those data, just like your local files and directories. So for example, for here, we can mount different storage system to one Elastic namespace and mount the Elastic namespace to our local folder. For example, the local directory Elastic here, it looks like it's just a local folder, but it could represent all the different cloud storage systems. So maybe one data set is a data set in HDFS, and the other data set, other folder, represents the data set in our S3 or Azure. So next we talk about like how to accelerate our cloud training with Elastic. After we knowing that Elastic provides such like unified namespace, POSIX API, and other functionalities. So for round one, how can we accelerate the under storage data access? So in this one, basically like sometimes our data set is already ready in our under storage, and we can directly use it for training. So in this case, our training may need to load the same data set multiple times repeatedly, and to do our training job, to tune the parameter or do other things. And in this case, if every training requirement or the data read or the like get files data costs, if all those costs need to go directly from under storage, that will create a huge basically a huge burden for our under storage, especially like the concurrency can be like a large amount of operations per second, and it will really make our under storage not stable. Some object storage may limit your access rate, and some HDFS and Ceph may be unstable and provide low performance. And in this case, if we can use Elasio to get the whole data set from our under storage once, and then store in Elasio to basically catch in Elasio cluster, and then provide to our training clusters. Then the data access will be much faster. Basically, Elasio is just next to our training cluster. And the more training cluster you have, the more training job you have, you can basically scale up the Elasio cluster or scale down based on your need. And the usage is relatively simple. We start Elasio cluster and we use one command to mount our S3 dataset, providing some of the S3 credentials, and then we can mount the S3 to our Elasio namespace. And then we can use one command to load all the training data into Elasio. And after the distribute load command, all the data located in our S3 dataset will be cached by Elasio and provide data locality for training jobs. So maybe that's a little too vague. So we use a concrete example. From Microsoft, they have more than 400 tasks need to read data from Azure and write data back to Azure. And the total data set is larger than 1 terabyte. And the total nodes is more than thousands of nodes. So previously, they copied the whole 1 terabyte data to each of the training nodes. And the whole read request could be much larger than 1 terabyte. And by using this approach, they are really easy to exceed the Azure's request rate, and Azure just say that, oh, I cannot provide you more data, so they just give you an error. And then basically maybe one or several of the copy job will be failed. And in this case, it's relatively hard for us to identify that, okay, which of the data set, which nodes didn't copy successfully. And then all the training jobs need to wait for all the nodes to have the data locally and data ready locally. So the GPU will be idle when we are doing all those operations. So kind of like the copy process is kind of like long and waste of our resources, and it's error prone. And what they do is that they use Elasio in the backend for the data catching. And by using Elasio, basically the training job didn't need to wait for our data to be ready local to start their training job. Elasio can asynchronously doing the data loading in the backend so that the training job can be started in the beginning and while waiting for data to load in the backend. So we can see from the left side graph, before using Elasio, the first a bunch of tasks are just waiting for data to be ready, and the last time, last maybe 30 minutes or maybe several hours, are also waiting for the data to be returned back to our cloud storage. And doing that, the data training is fine, but the data processing, data I/O operations, the stage of I/O read and I/O write makes our GPU utilization rate really low. And by using Elasio, because we are doing the streaming read and write in the backend, so we can see the GPU utilization rate is really stable from beginning to end. And because we're streaming the read requests and we reduce a lot of read requests, so we are unlikely to exceed the cloud storage request rate. So it's less error prone. Okay, now we talk about, after we talk about how to accelerate our cloud training and from cloud storage, basically how to accelerate the cloud storage read, and then we talk about how to combine the data preprocessing and training together. Remember, one assumption in the previous round is that our data set is already ready to be used in our cloud storage, but that not always be the case. We need to do many of the heavy data preprocessing, like the transformation or other stuff, like before we are ready to use the data set for training. So in this case, how can we use Elasio to combine the data preprocessing and training strategy together and speed up the whole process? And for data preprocessing, there are multiple ways. And first, we talk about how to use like Spark Flink to do some big data ETL, and then use training to use those preprocessed data. So for BossGP, they have a use case that they use Spark Flink to preprocess data, and they need to do model training on top of the preprocessed data. Their original solution is that they use Ceph. Ceph is a persistent storage. They write the preprocessed data into Ceph, and then model training directly read those data from Ceph. And multiple problems are found here. First, not only all the persisted data that persist to Ceph under storage, but all the temporary files, like the transformation file during the ETL stage, may have many temporary files, and all those files will also be returned to Ceph and cause Ceph under really high pressure, and those data does not need to be persisted. On the other hand, our training will keep reading data from Ceph, and especially like our training is really heavy. So one popular data set may be used for multiple training cluster, especially when we are training the parameters. And in this case, our Ceph will also under really huge pressure. And we cannot control the Ceph rewrite pressure, so the cluster is really unstable. And we always want our persistent data storage to be as stable as possible to make sure that our data is really safe. And so the solution that they are coming with is using Elastic in between our compute training and also our under storage. So basically, they use the sparkling to do the data preprocessing, and all the temporary file is written to Elastic, and all the persisted data, basically the data preprocessed result that available for our training, will be write to Elastic, and Elastic will be persist those data to Ceph and HDFS for long-term persistent storage, and those data set will be directly written to our model training. And the more model training, the bigger the Elastic cluster to support those training like burst workloads. And in this way, we can keep our under storage stable. So basically, in this way, we can improve our under storage stability. Basically, the temporary files will not return to the under storage, and also more training job. We have a bigger Elastic cluster to support the burst workloads. And we can speed up the whole process from data preprocessing to training. Our Elastic cluster can be put closer to our compute and training jobs. And as long as the data is ready in Elastic, our training job can be read data from our Elastic cluster. And Elastic can do the data persistence in the background asynchronously. So this persist data stage will not block our training jobs. And we can just launch more Elastic clusters or bigger Elastic clusters to meet the burst ETL or training requirements. And in the other case, sometimes we will use some C++ or Python, the scripts, to do our data preprocessing. And in this way, we can also use Elastic to speed up the whole process. The Elastic can help you to load data from different like under storage, and data preprocessing like scripts will read those data from Elastic, preprocess it and return back to Elastic and provide to training. And the same workload is really similar just to the ETL one. So it's seamlessly to our users. So in the last one, we talk about how can we speed up the data abstraction layer. So in this one, just no matter that what our data set is, it may be a ready data set in our under storage, or it may be need to do some data preprocessing using some big data ETL tools like Sparkling, or using some training scripts like C++ and Python to do some data preprocessing. All those data sets can be directly read through to load below by Elastic and provide the caching capability for our training jobs. So the training jobs can read the data repeatedly from Elastic to speed up the whole training process. And similarly for write, all the temporary files can be temporarily cached by Elastic for future usage, and all the persistent data can be directly write to Elastic and persist to different count under storage. You can also configure like multiple under storage if you want. So basically, Elastic can be used as a data abstraction layer for analytics and AI in the cloud. different compute, different chaining job, access data from different cloud storage. And Elastic provide a caching capability to move our data closer to our compute and chaining jobs to speed up the data access. So in Momo has multiple Elastic clusters, including like thousands of Elastic nodes, and storing more than 100 plus terabytes of data. And Elastic mainly serve the searching and chaining tasks of Momo. And Momo, they still continue to develop new use cases of Elastic, especially the chaining use cases. And they use us mainly because Elastic supports multiple under storage and multiple compute and training frameworks. In their case, they have different kinds of compute jobs and they want to persist data to different under storage so that they can easily switch from cloud storage A to cloud storage B or from one Ceph or HDFS cluster to another cluster. They can easily do those switch. And they use us to accelerate their compute and training tasks. I know that they want to make their user have super fast experience. So before we talk about all the detail, Momo is kind of the Tinder in China, basically. And by using Elastic, they can also reduce the metadata and data overhead of the under storage. They have huge amount of user base. Maybe similar to Tinder user base. So, and also like the Momo, they also develop some chaining use cases. They have used Elastic to do the billions of image chaining. They have like 2 billion small files, and their stack is the pure stack is PyTorch with Ceph. And now they add Elastic in between to reduce the metadata and data interaction with Ceph to improve the Ceph performance and also improve our data reading performance. And they also use Elastic to do some of the recommendation system model loading. Basically, they upload the model to HDFS and they directly load the model from HDFS to Elastic. And the recommendation system, they may have hundreds of nodes, and those nodes will directly load the model from Elastic concurrently. Considering that if the load is directly happening in HDFS, it maybe give HDFS a really huge pressure. But if they are loading from Elastic is thing that you can add and remove based on the needs. So they just add more Elastic cluster or add more nodes to speed out their system or model loading. And similarly, they use Elastic for A&M system index loading. So in summary, Elastic may help you if you have one of or multiple of the following cases. If you have distributed chaining, if you have just single node chaining with a small data set, you don't really need to use Elastic. You can basically just copy the data set to your chaining node and then do the chaining. It's super quick. So Elastic is helpful if you have distributed chaining and if you have a large amount of data set, especially when the data set cannot be fit in your local storage. Then you can use Elastic to do a distributed chaining to have a distributed caching cluster for your chaining jobs. And it's especially helpful if your network I/O cannot satisfy with your GPU requirement. So many cloud storage nowadays provide their cloud storage field solution, but their network I/O may not be satisfied. And also their cloud storage may have some request limit. And in this case, you may consider catching the whole data set closer to your training jobs to fulfill your GPU requirements. And we find especially useful when the users have multiple data sources and multiple training and compute frameworks. Basically, if you use Spark Flink for ETL and you use TensorFlow and PyTorch for training. In this case, Elastic can be a unified namespace and in between to connect the different like training jobs and compute jobs together. And if you have multiple data storage to read the dataset from, or maybe write the dataset to, then Elastic is helpful for managing those data read and write requests. And many users from us because their under storage is unstable, facing the high concurrent training requests. So they found us to reduce to basically make their under storage more stable, especially when meeting the burst requests, and also to avoid the cloud storage request rate exceed problems. And also like in the training job, maybe like maybe some companies, they have some data set they are really heavy. They basically use the data set for multiple training clusters. Multiple teams share the same data set. In this case, if the infra team provides some of the infra to could cache those data in another cluster for those like training tasks, that it can reduce under storage load, and also the data set can be shared by those different tasks, just like what Microsoft did. And in the end, I want to really thank our community. So this project, the Alacio POSIX API project, is not a top-down decision from the Alacio open source community. It's basically our open source users, they found us and say that, hey, our training job, they need to load some data from our cloud storage. And we found that the training job, the CPU basically is idle. We can only use our GPU to like maybe 50% of the GPU, and it's really low and it's unsettable. And they found us to say that, hey, we think that maybe Alacio can be used in this environment, can be used for training, because many people of you guys may not know that Alacio previously is designed for HDFS and for Presto and Spark for analytics workloads. And they found us to say that we think that Alacio maybe can use in AI training, and why not we have a try. And then we try Alacio in the AI machine learning scenarios. And in the beginning, it doesn't work that well, but we proved that it can be used. It can maybe improve a little bit of GPU, but not much, because because we are not directly designed for AI machine learning. But as the time goes, we iterate our solution with all those community users, and they give us idea of how they assess data through their training jobs, and give us feedbacks and iterate the product basically with us, and then to make this product gradually become more mature. And now it's in production in Microsoft, Shopee, Bilibili, Momo, and many of the open source companies. And for about how to deploy and use, feel free to check out our Alacio Day talk that available at alacio.io, Alacio Day webpage. And then on there, we have many talks to talk about like how to actually use Alacio POSIX API and how to deploy Alacio on Kubernetes, and all the other related talks about basically how to accelerate your compute job, your ETL job, and your training jobs. And for the POSIX API specifically, feel free to check the Alacio POSIX API webpage. Directly Google like Alacio POSIX API, and you can find it. And we have many of the talks like this one will be available in our will be shared in our Alacio website, alacio.io website, and share via our social media like our Twitter, Alacio, LinkedIn, and we have a Slack channel. And Slack channel is mainly for like technical discussion, and also when you have problems you want to get help from, then you can also like ask to talk to us from Slack. In Slack, we have like engineer from all around the world to answer your questions and to help you to figure out your problems and whether Alacio fits your need, and whether you have some problems running Alacio. Any questions or just talking, you can also like just talking to us through Slack. Any questions so far? That's it for the talk.
Yeah, thanks, Liu. Thanks a lot for such a great talk. And I don't think we have any questions yet. So, yeah, I mean, thanks a lot.
Friends, if you guys have any question offline, then just go to our Slack, or I think the Discord is really great. So I will also watch question there.